Hello. This is probably a first video of a coming series on real analysis, and it's not meant to be a very rigorous video, in the sense that you cannot rely on this video to systematically learn self-learn real analysis, but the purpose of this video is to offer some insights into the tools used in real analysis, and when to use them and why we use them. So without further ado, let's delve into the problem itself. So the problem asks us to prove that the set of points in the R2 plane, x, y, x is larger than y and is larger than 0, is open. This is basically the set bounded by this functional upper bound, y equals to x, and a functional lower bound, y equals to 0. Now, intuitively speaking, this must be open, right? Because it doesn't contain this boundary. But we have to be very rigorous here in a sense that we have to prove that for any arbitrary point chosen inside this region, there exists an open ball that is entirely contained within this region. Now, some of you may think, can we find a formula for the distance between a point and the line, and we then pick the radius of this circle, VR of x, y, and we make sure that the radius of this open ball is strictly less than the smallest distance from the point to the line. Well, I've tried that, but it turns out to be not very helpful, because the formula for the distance between the point and line can get really messy, and we're hoping that this formula would somehow lead to the inequality x larger than y. But at least I've tried, and I couldn't get it boiled down to this simple expression here. So it turns out to be not a very good method in general. And if you think about it, even if we were successful in proving that you can choose an open ball such that every point containing it is also in the set, what if we change this function upper bound to something instead of a straight line? For example, if I were to ask you that to prove that the set of all points bounded by the function upper bound y equals to fx and y equals to 0, which is this region, which is obviously still open, but the method here won't work very well here, because it's just really hard to find the so-called open ball and find the distance between the point and the curve. So it turns out to be not a very general method that you can use. If we want to prove this question in a very general way, in the sense that you can apply it to any functional upper bound instead of just fx equals to x. So let's rewrite our problem into a stronger statement, and we're now trying to prove a stronger statement that the set of points in the R2 plane xy such that fx is larger than y, larger than 0, is open. Okay, so the idea here is that intuitively the inequality fx is larger than y, this inequality should somehow lead directly to openness. But what exactly should we do to fill in the gap between our intuition and a mathematical statement? The idea is to think about how we would prove any region is open in general. Suppose you were given a region, let's say the open region one interval on R, of course, on R2. It's this topology product of the open interval 1, 4 and the open interval 2, 3. Now this is open because by definition of the topology product, if both of these elements are open sets, then if you take the topology product, then the region they form in R2 plane is also open. And if you think about it, what we're trying to prove is that for a region that extends, for example, indefinitely in both directions, it has a functional upper bound. We're trying to prove that this region is open on R2. But it's not the topology product of something, right? Because it's not rectangular, and if you have to say, this part of it looks like an edge, from negative infinity to infinity, this looks like an edge. But here we cannot find we cannot find a portion on the real number line that can give us the desired region through a topology product because it's curvy, right? It's a curve instead of a straight line, instead of constant. So the idea is to somehow transform this hard to deal with curve into a very simple function, a constant functional upper bound. Okay, and how do we do that? The idea is that we have to find an invariant because think about the nature of a constant upper bound. What do we mean when we say constant? It is that, for example, if you pick all the points with the same y coordinates on this line, they all have the same difference from the difference between the y coordinates and this function upper bound. For example, y equals to some constant k. It's a constant value, right? This distance is constant for all the points that have the same y value. But if you look at this point, but if you look at our example with a non-constant function upper bound, suppose we pick all the points y equals to k on this line. They have different distances to the vertical projection of onto this curve, right? The distance is different. So the idea is to make the different distance the same through some operation or some function. And if you look at the inequality that we were given with, which is fx is larger than y, it is strongly hinted that we somehow transform it into a way that we have a constant on the right. Because for the rectangular example, which is very easy, we have all the points are below y equals to k, meaning that y is smaller than k, right? We have a constant on the right hand side. Similarly, we want a constant on the right hand side for our example as well. So by now you must have guessed what we do is that we move the y term to the left to get fx minus y is larger than 0, and now we have a constant upper bound on our left through a function called g. So now we go ahead and we name this function g, such that it takes in all the points x, y, and it outputs a value, a scalar value, fx minus y, minus y. Now the idea is that this function should be able to cover all of the set that we care about. Let's denote our set as A, which A is the set of points such that fx is larger than y is larger than 0. And notice how it is the intersection of two sets, x and y, such that fx is larger than y. Intersection with xy, such that y is larger than 0. Now, this part is obviously open because it is the topology product of the real number line times 0 to positive infinity. Both of the real number line, the entire real number is open. You can find that conclusion anywhere. It's a very classical basic statement in your analysis. Excuse me. And you can, and this set from 0 to positive infinity with 0 exclusive is also open, which is very obvious. So we have that this set right here on the right is open. Okay, now for this set, we are trying to use this function that we constructed to define all of the points in the set. And notice how, since all of the set in all of the points in the set in this set right here, it satisfies fx is larger than y, so it must satisfy fx larger than minus y is larger than 0, right? So so this is the range of g. So fx minus y must be larger than 0. So all of these points right here are the points that satisfy that when you input them into this function g, the output is larger than 0. So the points itself, which are the inputs, we call them, the set of the input points are called the pre-image, right? The pre-image. The pre-image is basically a whatever gets mapped onto the range. And this is the pre-image of an output of the function. Okay, so we can rewrite the set as the inverse function of g, since we are going backwards. And the domain, which is the range of g, is from 0 to positive infinity, because for all the points that are below the line y equals to fx, it can approach 0 as close as it wants. It can also be as far as be as far down as you want it to be. So obviously the range here is from 0 to positive infinity. Okay. So now we want to prove that the inverse image of G of the set 0 to positive infinity is an open set. Well, how do we prove that? But here we use a very useful lemma, which is the inverse image, which is just the pre-image. They are the two names for the same thing. The inverse image of an open set is open. Now, perhaps I'll make a video on how to prove this lemma in the future, but for now, let's just use this lemma here to help to solve our problem. Okay, the inverse image of an open set is open. So this means that A is the intersection of two open sets. And this gives us A must be open. And that is what we were trying to prove in the first place. Okay, so that would be all of it for this video. And the lesson, the key takeaway here is that this construct from the construction of G is a lifesaver here, right? Because it sort of linearizes a non-constant functional upper bound. Functional bound, right? Thus, it turns it into a very familiar region that we can prove, which is that 0 to positive infinity, which is obviously an open set. And then we use the lemma to prove that the inverse image of an open set is also open. And finally, we have that the intersection of these two sets here is open.